Go ahead and get started. Good to see everyone here today. Where we left off on Wednesday. And I don't want us to belabor the point too much, so we'll just briefly review and then move on, was trying to get a little bit of a better understanding of where things are actually placed in memory in practice. Um, I think having that awareness will make you better at debugging the kind of memory-related issues that will inevitably come up as you are working with pointers. For the most part, when you work with arrays, you can kind of ignore that some of these issues are still there underneath the hood. Once you start to work with pointers and have pointer-related bugs and crashes, again, knowing the exact address that something is located at probably doesn't help you, but recognizing that there are these different address ranges of where things are placed in memory can, I think, help you better conceptualize what is happening as you create these pointer variables, as you use the dynamic memory allocation functions to allocate memory for those pointers, and as you move things around and pass things around in your code. This is probably sufficient for your mental model, thinking primarily of these two different regions of your system memory that you always have access to. For the most part, outside of when we've sometimes created global variables, we've been working with things on the stack. And I've used that term enough now that I think for now it's sufficient to think of that stack as being, here is the region of memory, this little rectangle, this block of memory that is relative to my function. I have one function that calls another function, function 1, function 2 in this example. They have two different regions of memory adjacent to each other in memory. That ties in directly to that discussion we've had a few times about the scope of variables. They're directly related concepts. I declare a variable inside a function. That variable's name only refers to one thing consistently when you're inside that function. That's a language feature. As an implementation consideration, it's because physically where that variable or variables get put are relative to where that function's memory space is allocated. And there's the kind of brief visualization here of, as you have a function that calls another function that calls another function, you're stacking these frames on top of each other. And then when you return from a function, you pop that most recent thing back off the stack. That's the case whether it is a function calling a separate function, or whether, as we'll see, even if you have a recursively called function, or a function that calls itself maybe once, maybe many times, we are able to distinguish between the variables defined in one instance of the function from those same named variables in the second instance of that same function, due to not the scope anymore, but due to the fact that they're in different locations in memory. That is how our stack generally operates. When we say put something on the stack, that's what that means. We can get pretty far with that, but generally there's a limitation that variables in a stack are kind of self-contained. As a function, I can access my own variables. I can't access other functions' variables without some trickery along the way. That's for the statically allocated things. Int a of 100, or just float xyz in my code. Those are all statically sized, so we can have the compiler generate code that figures out exactly how big every one of those frames need to be. That's useful, and we've gotten pretty far with that. We've started to see some of the limitations with having that static sizing of things, because sometimes we don't know until the program's already running. And not just sometimes, I would say a large number of times, a large percentage of the time, we don't know until the program's actually running how much memory do I actually need. I can do int a of 100 if I know I only need 100 integers for this part of the code. What if I don't know? What if it depends on some other things that may be happening in the code? That's why we need these other functions, this dynamic memory allocation. To avoid these two different kind of allocators from conflicting with each other, they are stored different ways and they're put in different starting locations in memory. For now, the actual implementation of how that heap grows and shrinks, it's not as straightforward. It's an implementation detail I think we don't have to become experts in now. I think for now, it's sufficient to have an awareness to say, when I use malloc, when I use these dynamic memory allocation functions, this stuff, these variables go somewhere different. My pointers are pointing to something generally within this range when I'm doing dynamic memory allocation. Stacks historically grow from high addresses back down in negative direction. Heap starts from low addresses and grow up in the positive direction. And the reason for that is to try to avoid them from kind of running into each other. But ultimately, let's say you have 8 gigs of memory or some physical limitation of how much memory you have or backing storage you have for a program. Eventually, if you allocate too much memory, you will run out of memory. And there's usually not a very good way to gracefully recover from when that happens. So we do have to become more comfortable with using these functions, and there's really just four, I think, for our purposes that we have to become comfortable with. I have it open just as under the C++ reference page we've been using. This is under the dynamic memory management tab within that. There's a few new ones that are kind of optionally supported. So really the first four are the four that we need. They are malloc, which allocates memory. Call it calloc if you want to. Allocates and zeros memory. Clear allocator, allocate and clear my memory. There's realloc, which takes an existing previously allocated block of dynamic memory and changes its size. Not necessarily bigger, not necessarily smaller, just changes its size. And then finally, there's that function called free, which deallocates previously allocated memory. That's the other aspect of working with the stack versus working with the heap. As we declare our variables on the stack relative to each function, when we call return from that function, that memory gets freed back up. That's just part of the convention, the calling of functions in C programs. When we declare our variables as dynamically allocated, as we're using our malloc or realloc or calloc functions here, it is our responsibility as the programmer. It's up to us to determine when we no longer need that particular variable or that block of memory that's being pointed to any longer. And I think I can only really, have you learn that through experience, because I think at first blush, your thought would be, well, it'll be obvious. It'll be obvious when I no longer need this array anymore and I can just get rid of it. But in practice, you have these pointers, you call a memory allocation function at one point in your code. Part of the value of these pointers is you're passing them all throughout your program. Different functions are making use of them. It's oftentimes not very clear at all without some careful consideration. When do I need to actually free the memory that I have allocated? And not freeing memory that you were supposed to free is a very common programmer bug, more generally referred to as a memory leak. And if you've ever run a program that is fine, someone else's software, that is fine when you first get started, nice and responsive, nice and snappy, you let it sit on your computer for an hour or a day or a week or some reasonable amount of time, and all of a sudden it's just slower and slower and slower and just less responsive and less responsive. There's a couple reasons that could happen, but one such reason would be effectively, at some point, probably pretty deep underneath the hood of that software, memory was getting allocated, it's no longer being needed, and it wasn't getting freed, and you have a memory leak. It's just using more and more memory over time. That is a pretty common class of programmer bug. It can be hard to detect those. Unfortunately, you can't avoid this issue by being too aggressive with the free call either. Because if you do that instead, if you free memory that you actually still need to use, and they go hand in hand, it's kind of a comparable type of bug, either not freeing something you're supposed to or freeing something you're not supposed to, and then using that pointer after it's already been freed. That is another class of bug that's referred to as a use after free bug. That's a pretty significant security vulnerability in most modern software. You wind up having a piece of your application having access to data that maybe it wasn't supposed to have because of when the allocation and when the freeing happened. So there's four main functions. Malloc, we've used a couple times. We'll play around a bit more with it just now. That's the basic one. Give me a number of bytes as input, return back out a pointer to an object of a particular type that you get to set. Then there's the calloc function that does something very similar, but if you know upfront that the region of memory you'd like to allocate, you'd like it to be all zeros, you'd like it to be all initialized to zeros, you may want to call that function instead. There's just a slight trade-off in, performance of just allocating a block of memory versus allocating a block of memory and initializing it all to zeros. We could probably write that code ourselves, right? The allocation part we would call malloc. The initializing to zero would be a for loop. Presumably, calloc is really well optimized to do that, maybe slightly faster than doing that ourselves. There's also realloc, which takes the pointer now as an input and resizes how much memory is allocated corresponding to that pointer. That syntax is a little annoying. In fact, you could argue for all four of these functions, the syntax is a little annoying because they're just all very slightly different for each example. If I go back to this page, here's the syntax for malloc. Its only input is a number of bytes. we've seen that it probably makes sense to use the size of operator to be very explicit. I want 27 ints, or I want 15 of these structures, or 32 doubles. You would do then 32 times size of double. You get back out the exact number of bytes that you're wanting. That's the syntax for this function. Just takes bytes as an input, returns that void star pointer, which then is your responsibility to cast to the actual type of the pointer that you are creating. That's malloc. Compared to calloc, which does something extremely similar. And for reasons I don't know, and I think probably historical reasons, it takes a slightly different syntax. It doesn't take a number of bytes as input. It takes a number of objects of an input, and then as a second input, the size in bytes of each of those objects it's taking as input. I don't know, maybe someone can find some historical record. Why is that syntax different than malloc syntax that just takes a total number of bytes? But it is. So you just have to have that in your mental map of how to call these functions. Instead of 32 times size of double as input to malloc, if you were calling it and having it being 0 initialized, you would pass 32 as the first input and size of double as the second input. And technically, the way it works, even if you got it backwards, it would probably still work, right? Because it's still just the total number of bytes that it's zeroing back out. Compare that to the realloc. That one, I think, for good reason, is a slightly different syntax because now you're modifying an existing dynamically allocated object that was corresponding to a pointer. So in fact, you pass it the pointer as input, and then you pass it in bytes what you like that input to be now. Previously, it was 32 doubles. I've now decided I actually need 33 doubles or 15 doubles, some different amount. You would pass in the pointer. You would pass in the number of bytes you would now like it to be. And the end result, similar to malloc, would be a pointer that's modified, that you then either update the existing pointer variable or create a new pointer variable for the new array that you have created. And then finally, there's function free, which is deallocating the space previously allocated by one of those other functions. And there it's just, you call free. Free my pointer. Free all the memory corresponding to my pointer here. Let's give it a try. So this is example dynamic mem in Replit. And right now there's nothing. We'll just start with int. So I have an int star A versus a statically allocated array of B. And we do know we can print our pointers, right? A is located at %p. B is located at %p. Takes an address, takes a pointer. How do we get a pointer for B? We could. There's a way to do that with the ampersand operator, with the address operator. B is an array. So how do we get a pointer to the first element in B? There's two ways. One is using the ampersand operator. We could do this. That's valid, by the way. Address of B is 0 is a pointer to the first element. When we have an array, I said this like 12 times on Wednesday. When you have an array, the name of the array is a pointer to that first element. That's why scanf with a string kind of worked by just passing the name of the array we wanted to update. But having said that, this is equivalent, and we showed that on Wednesday. But I'd say the more standard, correct way, it's an array. The name of the array is a pointer to the first element. We can run this even without A being initialized at all. The nice thing potentially about %p versus just %x to print it as hex is this has some mechanism for checking if it's a null pointer, and it should print out that it is a null pointer. Equals int star A, and it gave me an address. I have to think about that a little bit. Still, this example is for doing dynamic memory allocation here. So let's go through a couple of those functions. I have to think about that a little bit. Int star A, and it says A is located at that location on the stack. That doesn't seem right to me. There we go. And here it says nil. I don't know why it says nil versus null. That's Replit playing funky little tricks with us again. Why is it pointing it to somewhere valid? It's not clear to me why it should in that previous run. General assumption is if you don't initialize it, it would have a value of undefined or of 0. Let's now say we need 150 ints in an array. A can be the pointer for that array. So start with that. Okay, I'm overriding A. This function is returning a pointer. And it's malloc, if we're going to use malloc here, it returns a kind of untyped pointer. As best practice, we want to be explicit. That is a type cast we've added there. Treat whatever gets returned by malloc as an int star. That doesn't involve any conversion of values. It doesn't change anything. It's really kind of syntactical hints to tell the compiler, here is what we're actually doing here. Malloc, and we tell malloc the number of bytes that we want. But as good practice, and I do recommend you do this, I want you to think in terms of how many elements I want to allocate and how big each element is. I want 150, and each of those is an integer. So I'm doing a little bit of multiplication. Give me 150 ints. The input to this is bytes. Yes, that would be 600, but that's appropriate. Now we look at where A is pointing to, and we go back to that diagram of that heap starting at relatively low addresses, the stack starting at relatively high addresses, and you can kind of see it here. Maybe it's not that obvious, but there's quite a bit fewer hex digits in the A's address versus in B's address here. So B is at that stack, B is relative to function main, A is located at that location, and we can do all sorts of things now with that pointer. If I want to now have a function that initializes values, let's not call it A, a function that takes a pointer to potentially an array, and we probably have to give it a count, right? We need to know like how many of these things we should initialize. And we can write a loop that does some initialization. We've done this with other arrays before, but now we're passing these pointers around. We have this pointer called vals. We can in fact initialize it a lot of different ways. This way I'm going to currently show is maybe the most literal way to do it. I want to follow the pointer, and I want to set whatever is at that pointer to be, and I guess it doesn't really matter, I don't know, I times I or something, just some random value we're initializing it so it looks different. If I then want to go to the next pointer, I can tell it, go to the next pointer. That initializes at the input pointer. As I increment that pointer, it goes to the next integer, and the integer after that, and the integer after that. And if you want to be clever, you can do that all in one line. That's postfix increment. It happens after we access star vals. We follow the pointer, we update it, then we increment the pointer. Or you can do it in 2 lines if you don't feel comfortable doing it in 1 line. That is kind of the literal way of accessing that pointer using that same little star operator again, which says follow that pointer. Whatever address it's pointing to, 14952A0, set it to I squared. And then increment it, which we saw on Wednesday, that actually adds 1 integer next. So it doesn't add actually 1 to the value of A, it adds 4 to the value of A. Move along to the next integer and increment that, or set that to I squared. Move along to the next one, and move along to the next one, for however many we want to do. We initialize 150, maybe we allocate 150, maybe we only want to initialize 100. Another way, and so there's nothing wrong with this. This is kind of like the most literal way to use our pointer. Follow the pointer, set it to something. If you want to go to the next thing being pointed to, increment the pointer. If instead now we want to write a function that prints the values, and this will look pretty similar. And we can kind of copy paste here. Instead of that, we want to do like a printf of the values, right? For now, we don't have to be very clever. We can just do like %d and a space, and then print a new line at the very end. We don't have to make it look good or anything. Given that pointer syntax, vals, we can also recognize the fact that, not all pointers have to point to an array, but you can treat that pointer as pointing to an array. This requires us knowing that what is being passed to this function is a pointer that in fact points to a number of integers and not just a single integer. When we have that, we can get the same exact functionality as follow the pointer and increment the pointer by just accessing vals of I. Those two ways of doing it, I quibbled a little bit on Wednesday and said maybe the assembly code that gets generated is slightly different. From you as the programmer's perspective for now, those two methods, line 7, line 14, are equivalent to each other in terms of how we access that pointer. Give me the ith offset from pointer vals is all vals of I means. That's true if it was a statically allocated array. It's equally true if it's a dynamically allocated array. You have a pointer that, because we called malloc, points to a contiguous region of stuff. And you can use the pointer syntax. That's still, line 7 is perfectly valid here. You can now use, and probably it's easier for you as a programmer to kind of like work with it, you can use that array syntax as well. Give me the ith offset into vals and print that value out. And then we should actually probably call it. Oh, let's just print out the first 10. And there's our first 10 values that we're getting back out here. That is our malloc function. At some point, and here again, I think Replit may be having some security or safety considerations that are preventing me from really demoing this out. At some point I said, I don't want A anymore. I don't want the memory pointed to by A anymore. So I could free A. Give back to the system to be used elsewhere the 150 integers we allocated at this point. This is almost, in all circumstances, a bug. This is what I refer to as a use after free bug. I have freed A, but because I made a mistake, I am still printing the values. With Replit, it's not clear to me whether it will crash, which I think should be the correct functionality, or whether it'll print garbage, or whether it'll print some proper values. And the result's a little interesting, in my opinion. A little bit. That's underneath the hood of what free and later malloc are actually doing. Either way, it's wrong. Either way, it's a bug. And if you have garbage getting printed out, usually having uninitialized memory or improperly initialized memory is the reason. But depending on what you wrote in your program, that could in fact be a very subtle bug, right? Because it looks okay at first glance. And if you're only looking at the last, the last 50 out of 100 values, maybe it doesn't look like a bug at all, right? If I was only looking at those values, that looks like, oh yeah, my code's working just fine, but in fact it doesn't. It's not working correctly. You have a use after free bug. It just so happens memory didn't get cleared for all those entries, but just for a couple of those entries that you have there. You can also choose to decide, after I have allocated memory, I need to allocate more memory for that same pointer. That's that realloc function. It's very similar to malloc, but it takes two inputs. It takes the pointer you want to update, or start with, I think would be a better phrase, and the new size, the new number of bytes I want to create. So I could decide I want to reallocate A, and now I don't want 150, I don't know, maybe I want 250. This works for either a smaller value or a larger value. There's also no requirement that you update the same pointer. Maybe I wanted to keep, the original A pointing to wherever that was in, oh, I can't call that B though. I wanted to keep A pointing to wherever it was pointing before, and I now have a new pointer I want to update called C. That could take A as an input, and it can update that pointer. I would say that in my experience, it's more common to kind of update the same pointer, but it's not a requirement that you do so. What happens under the hood really depends on a lot of other factors, but conceptually what happens is it takes whatever region of memory you had, and it grows it or shrinks it. It should still keep the values that you previously had. And we can see what we have here, where we have initialized only 10, but we have the other values here that have been allocated. If we do that the other way around, if we initialize 100 and then shrink it back down to 15, that would still be a bug in my opinion. It's a little bit more subtle now, because now we're going past the end of a valid allocated region of memory. But again, what Replit decides to print really depends on algorithmically what's happening here underneath the hood for those functions. And the end result is what I would call a pretty subtle looking bug, right? Let's walk through one more time what I just did here, because we were just kind of messing around. Give me 150 integers. Initialize the first 100 of them. Change what I'm pointing to instead just point to 15 integers instead. Take this block of 600 bytes and make it 60 bytes instead. I could print out C as well and see whether or not it's the same location as what A was. And then take that pointer and print out 100 integers from there. That is a bug. That's not correct functionality here. What that bug looks like and why these can be so difficult to track down and really figure out is, well, there's no crash here. And in terms of my values, are they correct? Well, correct is not the right way to phrase it. We know there's a bug in the code. Does it print out I squared for I equals 0 to 99? Almost. That's pretty tough to track down, in my opinion, right? We oftentimes don't have enough data, or we have too much data that we can't print out every element in every array and really know if they're right or not. Remember for our sine waves, right? Everyone who came to my office hours for our sine waves, I said, well, I don't know if that sine wave is correct or not. I mean, it's got -1 to 1. It looks correct, but we have to plot it to even have a good feel for it or not. With this data, it looks pretty good. And then for I don't know what reasons, I'm not even going to hazard a guess. It looks good. And then there's 1, 2, 3, 4, 5 elements in the middle that have garbage in them. That'd be a pretty subtle thing to have to kind of track down. So the solution is not to create those kind of bugs in the first place if you could possibly do so. Out of curiosity, since I've now refactored the code accordingly, there's no guarantee, but we can print all 3 and see where C is located at. And in this case, we called realloc, and C is located at the same exact place A was prior. I don't think that's guaranteed to be the case, but maybe because we're doing so little memory allocation here. C is, since it's located at the same place, when I print values of C of 100, we get mostly A's old values, but not quite. And so that's where you have to be very careful with when you're allocating, reallocating, and freeing our memory here. You have to have a mental model going of what are my pointers pointing to and how much memory do I need at any given point in time. It's just something you have to kind of play around with. One of the Lab-08 examples is really, you're not really creating that roguelike game from scratch. You're really just looking at the existing objects and determining, am I allocating when I'm supposed to be? Am I freeing when I'm supposed to be? You're kind of just doing some pattern matching with that one. But as you start to work on more advanced programs, yes, ideally, if I knew everything could fit into 1,000, I don't have to worry about this at all. When you're doing a statically allocated array, none of these things are an issue. At least these type of things are not an issue. But for a lot of real applications, you don't know that 1,000 is what you need. Nor can you predict reasonably what the upper limit of what B size needs to be for your array. I mentioned this already, but when I was talking about memory leaks, this is a pretty common thing that you see in applications. Why, when you run a piece of software for 6 hours, it's so much slower than when you first potentially started it up. Again, you may look at this code and say, well, I would never do that in my program, but I'm hiding potentially thousands of lines of code and 50 files in these ellipses here, right? You have some critical loop in your program, some kind of resident loop that keeps your application running until it's eventually time to close out of it. And somewhere at some point within that loop, you do some allocation of some memory. If you do that enough time without actually freeing that memory, you'll keep using more and more memory over time. And in Windows, you can open up a task manager. In Linux, there's a half dozen ways to kind of monitor an application's memory usage and do that. Do that for a web browser open on a modern 2023 style website. Do it while you have YouTube open or whatever you're browsing, and watch and leave it on for days at a time. And watch as it starts to tick up. Now, the memory leaks they have are generally caught and detected and fixed, but even still today, there are still very subtle memory leaks that programs have. But if you do this in your own code, It may not be subtle. It may be very quick that you're just using more memory than what your system can actually fit in physical RAM at any given point in time. And you go from an application that's very responsive to one that's not useful, not responsive at all. This happens a lot. Again, it's never going to stare you in the face exactly like that. What's happening between allocating and freeing could be 50 different files, 300 different functions, and all sorts of different things that you're doing here. Yeah, if it all fits on one page of code, you could probably detect it and catch it. But in real applications, it's a lot more complicated in that we allocate things because we need them, and we need them in all sorts of different contexts. We want to share these pointers around in our code, and at some point, someone has to be responsible for freeing it and detecting when that happens and doing that only when that's needed. That's a challenge with working with dynamic memory allocation. And finally, when we went back to the motivation for this, I was talking about two-dimensional arrays for dynamically sized images. And I haven't exactly shown you how to do that yet. One approach that I saw some people do for back in Lab 7 even was if I need something two-dimensional, I can always just allocate an equivalently long one-dimensional or single-dimensional array instead. If I want an image of size n by m or resolution n by m, if I don't want to worry about it too much, I can always just allocate via a single pixel pointer, a single-dimensional array of size n times n. And then in your code, you have to kind of keep track of what your I versus J would correspond to. It's I times the number of columns plus J. And if you do that, then your code will actually work. It's a very common approach. It does make the programming to access that image a little bit more complicated than it would be otherwise. The other complementary approach would be to recognize that what we think of as two-dimensional array of data can in fact be just several one-dimensional rows of data that we can then allocate independently and allocate separately from each other. Technically, this is slightly less performant than this approach. It's a very subtle difference in performance. Here, we do one single memory allocation, and we do I times num columns plus j every time we want to access it. Here, we have to allocate a pointer for each row separately, and then to actually access array of I, j, we actually have to follow two pointers. So it's just a little bit more work that's required, but it's not enough of a performance difference that you really should sweat it too much. But if you want your two-dimensional array and to do so via dynamic memory allocation, your code is going to look like one of these two examples here. Both are fine. I think the trade-off here is, I guess, just keeping track of where I am in the image isn't as straightforward to me, at least. And if you're initializing everything to 3 or some constant, it's not that bad. But when you're applying a convolutional filter and you're doing a windowed transformation across an image, that code can get a little bit messy. There can be a lot of I's and J's and K's and L's and things like that in your code if you're not too careful there. But here again, recognizing that if we want an n cross m image, we can do so via one singular linear array. Alternately, we can recognize that we could allocate each row of the image separately, and what we wind up having instead of just an int star, a singular array pointer, we can have a pointer to a pointer. And once you see that pointer to a pointer, we've talked about a key in a mailbox that holds a key to another mailbox. It's still that. It's still a pointer to a pointer, but you can also potentially start to think of it as a pointer to a two-dimensional array as well. Each row would then be allocated via a mechanism by which we first allocate a series of row pointers. That's what that first thing is doing here. Let's break down syntactically what's happening here. Int star star image. Pointer is a variable that stores an address. Specifically in this case, this is storing an address of an int star. You can always put spaces between the two asterisks if you want to kind of separate that out conceptually, but conventionally this is how we would do this syntactically. This is a variable called image that holds a pointer to a pointer. So when I do a malloc with that, what I'm actually allocating is not a series of integers, I'm allocating a series of pointers. And here's the thing, because our pointers are oftentimes the same size of our integers, but not always, on some systems, if you do this part wrong, your code might still work. On other systems, it might not. But conceptually, what we should be doing is recognizing this is now a pointer to a pointer, When I want to allocate a series of row pointers for my image, the result is an int star star. I'm mallocating n, not integers, but n pointers. So n times size of int star. Give me not n integers, but give me n integer pointers. Give me a pointer that I can use to later allocate an entire row of that image. And then I have to go through and actually update those pointers to be something valid. Now, for each of my pointers I've just allocated, image of I, the ith pointer that image is pointing to, set that to be the result of allocating m integers. Give me an entire row. Give me the 0th row, then the 1st row, then the 2nd row, then the 3rd row. When you set it up that way, now when I later on reference image of I of j, this follows the first pointer, this follows the second pointer. This updates effectively a two-dimensional array of memory that you've then allocated, that you can then just reference like it was a statically allocated two-dimensional array. But this is a pretty advanced example. Do this when you need to, and for image processing, we oftentimes would need to, but just recognize that's what this is happening here. If I have an int star star, my pointer is itself to an int pointer. So if I was going to allocate something for that image variable, it should be an int star star pointing to an array or a singular pointer itself. I've allocated a pointer or series of pointers. Let me just suggest that this example may not make perfect sense for you yet, but make a mental note of look back on slide 27 for how I want to allocate two-dimensional data. Again, if you statically know how big it is, you don't need to do any of this. But if it's a system for which you don't know how big it's going to be, the Minesweeper example, where you can specify at runtime how big do I want the Minesweeper game to be, that would be allocated via dynamic memory allocation. And finally, just a little syntactical thing to be aware of is that we've talked about structures as being a valid, necessary thing to have in our programs to structure the way we think about our data and to simplify the type of things we have to pass around. So like any other of our built-in kind of native data types, you can also declare pointers to our custom struct type to do the same thing with our struct variables as we do with our ints or any of our other variables. But we have both things that we have to be aware of. We talked about previously, we have structures of arrays or an array inside our structure, like first name and last name. We also have arrays of structures. Give me 47 students. It's the same thing with pointers, in part because of that pointer array equivalence concept. We can have pointers in structures, or structures with pointers, or structures of pointers, and then we can also have pointers to structures. And how we deal with that is something we have to be a little bit careful as well. So when you have a student data type, like we had previously when we were talking about this topic, you can declare pointers to variables of that type. Give me a pointer to a student and maybe two different pointers to a variable of type student data. You can then use the ampersand operator if that's relevant for your purposes. You can dynamically allocate an array of 15 students. Let's look at that syntactically again. Student pointer. So we're going to cast the result of malloc appropriately. We're going to allocate 15 times the size of student data. And the nice thing is, just like for size of int, the compiler's going to be able to figure out size of student data. However many bytes this is, well, it doesn't matter. And if you change it tomorrow, the rest of your code still works. If I decided that I actually need 64 characters for first name and last name, the compiler will recognize that the size of student data has grown and it'll allocate the right amount of memory for you. So syntactically, while it looks a little bit more foreign to us perhaps, it's doing the same exact things when we allocated 150 integers in that example. Likewise, if we have some other pointer, we can still use that address, that ampersand operator, to explicitly get a pointer out of an existing allocated thing here. We have to actually follow the pointer first when we want to access an individual component of our struct. Then we use the dot operator. Then we use the component selection operator. This looks a little messy, but this is conventionally how one does it. You follow the pointer first, and then if I want to access the quiz score for, in this case, the 7th offset student, the 8th student in the class, you follow the pointer first, then you use the dot operator. That is such a common thing that we have to do all the time because we have structures in most of our programs and we have pointers in most of our programs, that there's a separate operator in C, and there always has been, specifically to do exactly that. So when you see that arrow operator, and that's how I want you to kind of visualize what that's doing, that's not minus greater than, though it does kind of look like it. That's the arrow operator. That's saying I have a pointer to a structure and I want to follow the pointer and grab a component at the same time. So pointer to a structure, arrow, give me the quiz 1 score we have for that. And if instead you did the dot operator, you would get a compiler error, and that's why that would be the case. Sometimes that can be a little bit tricky in our programs because sometimes we have statically allocated things and other times we have dynamically allocated things, and we swap between two all the times in our program. You do have to be aware of it then, that when you're dealing with something that is a pointer and it's a structure, you need the arrow operator. If not, you can stick with the dot operator here. This example is doing two things here. It's a little bit ugly. So this example is doing both a pointer to a structure and a pointer within a structure. Just like your question, so stretching. Just like with our images or any other data, we may not know what size it needs to be until it's time to create that object. There's no reason that can't also be the case for our structured variables as well. So in this example, the main change between this and the prior student data structured data type is for our first name, perhaps either we want to minimize our data usage or we actually don't know how long our student first names are. Some of you have very long first names. So in that case, we would do the same thing we would do with our image pointer, which is to say, I know eventually I'm going to be pointing to an array here, but I can't do it yet. I don't actually know how long that first name is going to be. So we have a pointer within our structure. And then separately, you can have a pointer to a structure, which is what's happening here. So let's walk through this code here. We have argc and argv. We're going to allocate 15 students. We're going to manually update the 7th student or 7th offset student, that pointer to point to that one. If I wanted to run this code and pass as argv1 the first name of a student, well, that tells us what we need to know in order to allocate the memory for that first name variable here. So let's say, for instance, I want to update the 7th student again. We can do it in one of two mechanisms. In this case, given that pointer to the array of students, give me the 7th one. I've now used the array syntax. What returns from that is a single struct. So struct pointer of 7 gives me a single structure. I can use the dot syntax for that. I'm not passing a pointer. I've used the array syntax. I'm getting a single student data structure, dot first name. But dot first name is a pointer inside that structure. If I want to now allocate enough space inside that first name array to hold the first name that's passed via argv of 1, I would then have to call malloc and return and update that pointer itself. So assuming I pass Joseph on argv of 1, I need to figure out how many bytes I need to allocate. I can use the string length function, which returns the number of bytes before the null character. As I allocate first name, I need that extra byte for the null character. So the new length or the new size, I want to add +1 to that return from string length. If the input was David, D-A-V-I-D, 5 characters, I need 6 bytes to actually store the result as to what's pointed by first name. I would then call malloc on that. I could then call string copy on that. The destination is that pointer. The input is a pointer that's argv of 1. I can then update other stuff here as well. When I access that same structure via just a pointer to that structure, I would then use the arrow operator. So here, printing out student %s got scored %d, I am following that pointer. It's a pointer to a single value via that arrow operator and not the dot operator, because now it's just a pointer to a structure. This one I'll run from the command line. We had to figure out how long that first name needed to be. Again, if we so chose, we could have written a version of this that instead did this. No dynamic memory allocation, and assume, just like we did with last name, assume 32 bytes is enough for everybody. And that would work. Should get the same result. Student David got score. But then what happens if our student's name is in fact, what's a sufficiently long name? You know, David, 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 David. Hey, I don't judge people. That should be more than 32. There's the student's great name. And oh, the semicolon's killing it. I can't, you cannot have semicolons in your name at this university. There we go. Null would work. Was that really not 32 characters here? That was more than 32. We have a nickname for him. We just call him Dave for short. And it worked. I do wonder where the rest of that memory wound up getting placed. You have a buffer overflow in this code. Let's instead, you know, the fact that Replic's papering over some of the issues is not really my concern for you. Let's instead do this approach, which is no matter what we pass as input, we check how much data we actually need. That's the difference here, right? We're saying, hey, whatever we passed as argv of 1, we need that many bytes. And in fact, because of this whole issue about making sure we null terminate our C strings, we need that many bytes, and we actually need one more byte. Whether you store that as a variable or not, or whether you put that directly in here, it's nice to store it as a variable so you can kind of debug that variable separately. Give me however many I pass, plus one more to store that null byte. Now when I have that pointer within the structure, allocate exactly that many bytes. Consequently, when I do the string copy, there should be sufficient, exactly the right number of bytes. String copy also copies over the null byte to overwrite that first name pointer. And now when I print it out, it should, not that it didn't work before, it should work and not have any kind of memory leak associated with it. And it works as expected. Again, this example is a little subtle in terms of what I was doing here. We set up 2 pointers. One, I decided to treat basically as a pointer to an array. I did an allocation of 15 students. When you do so, you can use that array syntax, right? And say, give me offset 7, give me offset 8. When I do that, what returns back out is a single structure. So when I do so, I can use the dot operator. But if instead I didn't want to use that array syntax and wanted to explicitly set up, as I do here, a pointer to that 7th object, I could still do so. But when I would access string data pointer 2 instead of string data pointer or student data pointer of 7, I can still do so, but because it's a pointer, I need to use that arrow operator. So those 2 things are equivalent. And this wouldn't change the correctness of the code, although I think it's definitely harder to follow because of it. Let's leave things here for today. Good luck as you dive into Lab 8. Have office hours if you'd like to see me, starting right now.